Terbufoes. Terbufoes is a chemical compound used in insecticides and nematicides. Terbufoes is part of the chemical family of organophosphates. It is a clear, colorless to pale yellow or reddish-brown liquid and sold commercially as granulate. History. Terbufoes is used on various crops including bananas, beans, citrus, coffee, groundnuts, sorghum, potatoes, sunflowers, and maize's soil cover to combat wireworms, mossy beetles, beet flies, and the black bean louse. It is not approved for use in the European Union. Also, the World Health Organization classifies Terbufoes as a Class I compound, meaning that Terbufoes is extremely hazardous. The maximum residue limit in the European Union is 0.1 mg/kg Terbufoes for most crops and animal products. The compound was first registered in 1974 in the United States, together with a United States patent of organophosphates for use in corn fields to deter corn rootworms. Between 1987 and 1996, an average of about 7.5 million pounds, about 3,400 tons of the compound was used each year. In November 2006, BASF sold its global Terbufoes insecticide business to American Vanguard Corporation. Organophosphate poisoning is not common in the developed world. Most cases of Terbufoes poisoning occur in the developing world, where protection against pesticides is scarce, but compounds such as Terbufoes are widespread, uncontrolled by a government, and readily available for farmers. Available forms. Terbufoes is available in granules for application in the agricultural sector. The compound is applied at planting in a band or on the seed furrow directly. Structure and reactivity. Structure. Terbufoes, also known as S-tert-butylthiomethyl O-diethyl phosphorodothioate, is a compound classified as an organophosphate. Terbufoes consists of a central phosphorus atom surrounded by 4 different groups. This central atom is surrounded by 2 ethoxy groups, 1 double-bonded sulfur atom, and a tert-butylthiomethanethiol group. Reactivity. Terbufoes is practically insoluble in water, but can be dissolved freely in organic compounds. It decomposes after prolonged heating at 120 deg C and can be hydrolyzed when exposed to strong bases pH9 and acids pH2. Synthesis. The 3 main compounds that are used for producing Terbufoes are diethyl phosphorodothioic acid, formaldehyde, and tert-butylthiol. Formaldehyde acts as a carbon donor between the diethyl phosphorodothioic acid and tert-butylthiol groups in order to link them. A secondary product of this reaction is water. Mechanism of action. Terbufoes, like other organophosphates, inactivates the acetylcholinesterase in humans by phosphorylation of the hydroxyl group of serine present at the active site of the enzyme. Metabolism. Metabolism in animals. The major excretion route of Terbufoes in lactating goats is via the urine. 96.0% and 86.9% of the administered compound was excreted through this route. Neither Terbufoes nor a phosphorylated metabolite of the compound was found in milk, and no phosphorylated metabolite was detected in the tissues. A low concentration of Terbufoes was detected in the liver and the kidneys. Terbufoes is extensively metabolized, judging from the low levels of Terbufoes and its metabolites detected in goat tissues. A proposed metabolism pathway of Terbufoes suggests a hydrolysis of the thiol-phosphorus bond, and enzymatic S-methylation, desulfuration, and sulfoxidation occurred in succession. In rats, the proposed metabolism pathway includes more steps, while the metabolic product is the same as proposed in goats. The mechanism in rats includes extra steps in the metabolism of Terbufoes and includes more metabolites. Biotransformation. Terbufoes is activated by a biotransformation to a sulfone compound. This conversion can take place in the cellular environment, but also in exposed organisms using the cytochrome 450 action. This conversion process makes the molecule much more efficient in binding with a CHE. The converted form may be significantly more toxic to amphibians than the parent compound. Toxicity. General toxicity. Terbufoes can enter the body through dermal absorption, skin contact, by inhalation or ingestion of the compound. Studies have suggested that the human null equals 0.9 mg/m3. Metabolite toxicity. 2 metabolites of Terbufoes have been tested for toxicity. Terbufos sulfoxide and Terbufos sulfone both inhibited cholinesterase activity, but did not cause any mortalities in beagle dogs. Health effects. Acute effects. Terbufoes can induce death by causing an acute cholinergic crisis ACC. Due to the irreversible inhibition of the SCH, the enzyme by the compound, acetylcholineage can no longer be sufficiently broken down by the SCHE. This results in excess, which causes overstimulation of the neuromuscular junction. The inhibiting effect of Terbufoes on a CHE works on the peripheral muscarinic, nicotinic synapses, and the central nervous system. The onset of an ACC can vary from minutes to multiple hours post-exposure. Symptoms of a Terbufoes-induced ACC result in muscarinic diaphoresis, vomiting, meiosis, salivation, nicotinic pallor and muscle weakness with respiratory failure, and CNS poisoning, headache, dizziness, altered level of consciousness symptoms. The toxic effects can be managed by early recognition of Terbufoes poisoning, rapid decontamination, and treatment with atropine or oxone compounds. Long-term effects. Long-term exposure effects, which are specific for Terbufoes, effects generally associated with organophosphates, OP not included, are the development of lung cancer, leukemia, and non-Hodgkin lymphoma NHL overall, as well as specific NHL subtypes. In males, an increase in aggressive prostate cancer has also been observed, while in females a non-significant increase in breast cancer can be seen. No genotoxic effects were detected in vitro and in vivo. No developmental abnormalities were noted in research, but a reduced fetal body weight was observed in mammals. Detection. The amount of metabolites caused by hydrolysis in vivo of an organophosphate compound such as Terbufoes can be detected in the urine using gas chromatography and combined gas chromatography/mass spectrometry (GCMC). Usually it is necessary to preserve the sample of the urine by addition of chloroform, to concentrate or extract the metabolites and to convert them to suitably volatile derivatives. The detection can be useful to determine patterns of exposure, but the levels of metabolite alone cannot be considered a guide to hazard.